Can you hear me at the back? Okay. So we'll first see where we were previously. In the first week, we saw how to collect the data. We also looking at different APIs. We looked at HTTP, GET, POST, different methods. Once we had collected the data, we looked at how we can validate and clean the data. Folks, can you please be quiet now? Once we have collected the data, we want to validate and clean the data. So here we were looking at things like missing fields. We were looking at if the schema was correctly followed or not. We were also looking at things like if perhaps some keyword was misspelled. In the most recent lecture, we looked at how we can label the data. So we looked at tools such as Label Studio. Importantly, beyond the tools, we also looked at, can you please turn off the laptops, everyone? Okay, how we can label laptops, please. How we can label the different kinds of tasks, where we looked at segmentation, where we had looked at object detection, some tasks for text, some tasks for vision, some for videos, some for simple binary multi-class classification. Today we are going to proceed further. So last time we had assumed that we'll have a human or an expert annotator who will annotate the input data. But we need to see how to scale that better. Imagine if you have 100,000 samples. Can you have a human being label those? Probably not. In terms of both the time required, the cost required, so the scalability is not there if you have a single human label all of the inputs. So therefore, the traditional approach or the naive approach might be get all the unlabeled data, label it all by yourself, which is by yourself means expert human annotator, and then train the model. So even before we get to the training of these AI models, we are stuck with the lack of data, of the labeled data. So what do you think we can do to mitigate this issue? We have 100,000 samples. We clearly cannot have a human label all of these. What could we do to make it better, to reduce the burden on the human?
Some of them can be trained by human and then they can be fed to a machine.
Some of them could be trained by human and then they could be fed to a machine. What will you feed to the machine?
The remaining samples that have to be for labeling.
But how will the machine label it?
Based on the feedback provided by the machine.
Okay. So what he is mentioning is that you label some samples, after that create a model, and then let the model predict and then use that. But is that correct?
But we are trying to make a data set so that we can train further models.
Yes.
We need a correct data set for that.
Yes.
Currently the correctness, if we gave it to a machine learning model just to create the data set.
Yes. So therefore you're stuck. Can you see the problem? If we label some samples, we give it to the machine, and then machine means we train an AI model. After we train an AI model, we ask the machine to predict, and we say that is the correct label. That is not going to work because the label could be wrong, the prediction could be wrong, and you're trying to create an accurate data set. But this is getting you somewhere. We need to make some tweaks around this. Other ideas? You can have a crowdsourcing platform, you could be using some of them, and you hire multiple of them, 10, 12, 30, 40, something of that sort. That will still remain very expensive. What else could we do?
Label most important data.
Okay, good. Label most important data. Use some kind of self-supervised learning. So we have not yet spoken about self-supervision, so I'll skip that. But just to give a hint to what we meant by self-supervision. So let's say that if I have an image. Now the classification task for this would be whether it's a cat or a dog. Perhaps I don't know this. But say if I do a deterministic transform, I rotate the image by 90 degree or 180 or 270, Do I know by how much I've rotated? Yes, because I have done the transform. So we can have a pseudo task or a pre-task which was to predict how much we have rotated the image. That is known as self-supervision. We will not get into that for today. But the point Shreyans was making was correct. We have to figure out which are the important samples to label. Perhaps not everything needs to be labeled. And we'll see how we can create some criteria for that. We'll be looking at 4 different variants today, or 4 different ways of attacking this problem. The first is called active learning, where we figure out which are the hardest samples which we need to have the expert labeler label. Second, we will create something known as weak supervision, which are some very simple rules, generally rules of thumb, which we will encode as some functions, which we will be then using as manual labels. Third, can we use LLMs for labeling now? We have very powerful LLMs. Many of them are now openly available running on your laptop. And third, we want to see that once we have done all of these strategies, or if we are given any public data set, could our system also be having a lot of noisy labels? Could it be having wrong labels? Can anyone tell me situations where you might have some wrong labels assigned to any, let's say, image task, a classification task? Okay, one image might have multiple labels. It might have a cat and a dog both. What else could be there?
Maybe something could be in the background that might be impacting the label.
Okay, you have something in the foreground, you have something in the background. So the task for the human who is labeling also becomes hard. There could be some genuinely very hard samples, something which looks like something between a cat and a dog. So there can be all of these cases which lead to wrong labels. We have to somehow detect them, fix them, before we feed them to the machine learning pipelines. We'll first start with active learning. How many of you know how to drive a car? How many of you, so keep your hands up, keep your hands. How many of you can do a reverse S? Reverse S. So make a S curve while reversing the car. A very small subset. This is, by the way, the test sometimes they use when people are genuinely trying to clear the test. So a very small subset of people are able to do a reverse S. So if you drive at 100 kph on the highway, is that helping you doing a reverse S? No. So what do we need to do in order to do a reverse S? Do a reverse S. You need to practice in such situations. So therefore the question is, if you keep on trying in very simple conditions, and then you're suddenly put in a very heavy traffic situation. If you keep driving in Gandhinagar and you're told to drive in the heart of Ahmedabad, you'll have a hard time until unless you've got any experience. Similarly, so the idea is we don't want to be wasting our effort and time on labeling easy examples. We instead want to be putting more effort towards the harder examples or the harder cases. Let's look at this example for instance. So this is a binary classification on 2 features. We don't know them yet, but we are just trying to distinguish between the 2 classes, the green class and the red class. If I keep on labeling examples which are very far from the decision boundary, from the boundary, is that adding any benefit to it? No. Is it not more important to label this example and this green example and this red example? Because this is where we have some amount of ambiguity. Therefore, this is what we are proposing. We will figure out which are the harder examples and label them, as opposed to trying to label everything. Similarly, for some text examples, if the examples are very trivial, the movie was very good, the best film ever, this is not really a very informative example. It's a simple example. But if you have certain harder examples, the movie was interesting, this is where you might have either it's a positive or negative, and that is where you might need some human expertise. So therefore, the idea is that we will skip some of the easy examples. We want to get to the harder examples quickly. Let's look at another example of 3s versus 5. Depending on how bad your handwriting is, sometimes your 3 and 5 would look similar to each other. So here we have drawn with respect to two features, the roundedness of the loop and the curve angle. These are just some arbitrarily written features. So some of the 5s which are written very clearly will perhaps be in this part, and some of the 3s which are written very clearly will be in this part. So these are very clear, there is no ambiguity about them. But if you look at some of these examples, is it a 3 or a 5, or some of these examples, this example specifically, is it a 3 or a 5? You'd require more inputs, you'd require expert labeling. So that again, we would want to label these as opposed to labeling these very simple examples. The active learning method is a very simple loop. You start with something known as a seed data set or an initial training data set. You label your model on that. You then have to have some notion of scoring. Which of these examples, if you look at, maybe there are these 100 images. I want to give a rank to these 100 images. Which of them is the harder example, which of them is an easy example. So I'll give a rating from 1 to 100 to these in terms of the hardness of the example. Once I have that, I will select the most informative one or the hardest one or the most uncertain one. We look at a few definitions of the most informative and then get them labeled, add to the training data, and then repeat this loop. The idea remains that in fewer samples, we will get the model to see harder examples and it will improve quicker as opposed to just labeling many examples. Yes.
So like if we are only judging the harder examples, isn't there a possibility that we'll miss the general trend itself?
Okay, good. There is a question that if we just pick up the harder examples, is there a possibility that we will end up missing the general trend? What do you think? We would expect the system to be always correct on the simpler examples, but it does not mean that we should be skipping those. So therefore, we'll come to this at the end of this lecture also. When we mention the seed data, we assume it has enough of the technical term of what you were mentioning is known as representative examples. We have seen enough of the representative examples. Now we will be working with the harder examples. So therefore, if the seed data set is very small, what can you say about the model? If I've just given 2, 3 images, is the model a strong model? If the model is not strong, the model's prediction will also not be very good. And if you use that for scoring, that will also not be very good. So therefore, we need a fine balance between what we say as the initial label data and then figuring out the most informative and uninformative samples. If we look at these examples, amazing films, so we are looking at this classification of the sentiment of the movies, positive, neutral or negative. If we look at the first one, amazing film, largely positive, probably no need to label, should be very trivial. It is these ones, interesting, which has a positive probability of 0.45, negative of 0.45 and neutral of 0.1, and not bad 0.48, 0.04, 0.48. So just looking at the top table, don't look at the bottom table. What do you think can be a metric or a method which you use to define the uncertainty or the hardness of a sample? So what do you observe in the first, what do you think is the difference between the first and the last example in terms of the probability scores?
Distribution of the probability.
Okay, the first one has almost all of the probability mass at just one class. The last one seems to be spreading it across the 3 classes, actually not across the 3, in this case 2 classes, right? So therefore, if you look at the first strategy, which is uncertainty strategy, it does 1 minus max of the probability. So if you do 1 minus max of the probability, in this case you will get 0.05. In the second case you will get 0.05, in this case you will get some number. So that's one way to understand how simple an example is. In the last case it will be 0.52. So it's a big number. So therefore, this last sample is a little uncertain. This is one method to understand this. The second method is looking at the margin. The margin means the difference between the most probable and the second most probable class. So that is telling you how confused I am in my top 2 recommendations, predictions. So if you look at the first example, 0.95 is the probability of the positive, the P1, and P2 is 0.03. The difference is 0.92, very significant. So this is perhaps an easy example. Whereas if you look at the last example, 0.48 and 0.48, you are almost equally likely to predict either of these 2 classes. So therefore, you are very confused between them. Therefore, this is a good sample to label. So in margin, if the margin is small, or the gap between 2 most probable classes is small, that is a good candidate. Third one is known as entropy. Some of you who have taken more advanced courses would already know what entropy is. So therefore, you should know the formula. Think of entropy as just so if we have a very uniform distribution, which means all of them are very equally likely to happen, that will have a very high entropy. And if we have a peak at any one of them which is very strong, let's say for this one, the entropy or the disorder would be very small. So if we just try to visualize these curves, which is the uncertainty and the entropy, I am visualizing this for 2-dimensional case. 3-dimensional would be harder. We will have to look at a simplex. So if we look at this graph, where we are just plotting on the x-axis probability of the positive class and the uncertainty score. So at the leftmost point, probability of positive is 0, probability of negative is 1, the uncertainty score is 1 minus the highest probability class, 1 minus 1, you get a 0. Similarly, when positive probability is 1, probability of negative 0, so therefore the most probable class has a probability of 1, therefore the uncertainty score is 1 minus 1, which is 0. It is at probability of positive equal to probability of negative equal to 0.5, where you have the maximum uncertainty. And you can notice that the shape of this curve is linear, it's a triangle, you get a triangle. On similar lines, when we draw the entropy, this is not a triangle, you will get this shape, this parabola-like shape. It is again the entropy is 0 when you are certain that it's one class or the other class, and it is maximum of entropy equal to 1 for when the probability of positive and negative is the same. So in both the cases, when both the classes are equally likely, that is when we have the most uncertainty. So can we have, so let's say that we were to choose these different, we call them acquisition strategies or heuristics. These ones that we are seeing, uncertainty score and entropy, these are known as acquisition or heuristics. Can we have, if we were trying to figure out, maximize one of them, can we have different examples being triggered by different acquisition strategies? Can we have one example which turns out to be most informative as per uncertainty score, but is not the most informative as per entropy? Can we have that? Let's look at these examples. The first example is 0.8, 0.1, 0.1. Probability of the highest class is 0.8, so therefore the uncertainty score 1 minus max p is 0.2. Similarly, the uncertainty scores are 0.5, 0.6 and 0.66. So if we were to look at only this criteria, then example 3 is the one which we would say we should be labeling. But if we look at P1 minus P2, we get 0.7, we get 0.01, 0.05 and 0.01. In that case, you would want to either label example 2 or example 4. And if you take the third case, entropy, which will be calculated, minus summation of minus p, log base 2, we'll get 0.92, 0.69, 1.53 and 1.58. In that case, you'd probably label the example 4, which is very close to the uniform distribution in 3 classes. So therefore, 4 examples, 3 different acquisitions, we end up choosing 3 different examples for them as the most informative one. If we look at the algorithm mathematically or the pseudocode, we'll start with a small unlabeled data, small labeled data, which has both x and y. X means the features, y means the labels. And we have a very large unlabeled data, which we call as the pool set, which only has the x associated with it. We don't have the y associated. We are trying to get the y. We typically have a query budget. How many queries can we get labeled by an expert? The loop is quite simple. You first label the model on the, sorry.
Could you go back a bit? In this case, why would you choose 0.60, right? Even though 0.60.
So in this case, we'll choose 0.60 because the most, you're uncertain about the uncertainty. No, so in this case, we'll choose this example 3 because the most likely class is also not very probable. So that is the intuition behind 1 minus max p. You say that the most probable class also has a probability of 0.4. Maybe we are not very sure. Therefore, label that. Sorry, one at a time. One at a time, yes. So then it's a mistake. It should have been 0.66. Yes, thank you. Thank you for pointing that. It should have been 0.66, should have been labeled. So in that case, this specific example will get triggered for 2 such acquisitions. And if we look at the type, maybe even for 3. But this is just to show you that there can be scenarios and one of them will be chosen by an acquisition function and not chosen by another acquisition function. Typically in practice, you would see all of them to be similarly aligned, not too different from each other. There was another question. Okay. So once we have the labeled data set, we train a model M on that. For I in 1 through B, which is your looping over your budget, you will select each x in the unlabeled data set. You will get the uncertainty for that. Now, how we get that? We will have to again step into the machine learning to understand how we get the uncertainty out of a model. For now, the simplest notion of uncertainty is just the probability of the 3 classes, and 1 minus p max gives you the uncertainty. Then you get the human label x, y star for that sample x star. Once you have x star, y star pair, you have a sample, you add that to your training data set. So you do L equal to L union x star, y star. This is a symbol to mean you are adding this sample to your label data set L. And then you do U equal to U. What does this symbol mean? This divided by in set theory. We do subtraction from this set. So we remove this sample from the pool. Why do we remove this sample from the pool? So definition of pool is unlabeled data. We have already labeled this x star, y star sample. We move it from the pool to the labeled set. And the pool set will therefore reduce by size 1. The label set will increase by size 1. Now if we are trying to, and this we just keep on looping till we have the budget. And in Python, this might be something like this. You have a model, you train it on the initial data set. I'm doing pool equal to x unlabeled dot copy. Why are we doing a copy? So once you implement this, you'll realize you'll have to get a little bit more understanding of the Python intrinsics. You'll have to understand call by value, call by reference also. You will also have to ensure that you're not modifying things which you should not be, or you vice versa. But those things aside, the quirks of Python aside, we get the probabilities on the pool set. You get the uncertainties for the pool set. You just get the argmax, the location at which the sample for which the uncertainty is the maximum. You get the human label for that, and then you add it to the training data set. Any question in this basic loop? Okay. So when we think about active learning, we'll have to think about this kind of a graph, where importantly we can look at this kind of a graph from 2 angles. The x-axis is going to be the number of labels from the pool set which we have labeled, accuracy on some known set. So in all methods, we generally expect as the number of samples increases, the accuracy will increase up to a point. If the training data set is very small, the accuracy will likely be poor. If we keep on increasing, the model will keep getting better up to a point. It also depends on the method that you have. Now, we see that both these curves start at the same point, which is a good sanity check. When you had not labeled any example, your model was effectively the same. Now, if you add some samples randomly, which is shown in this blue curve, instead of choosing it as per our method, if you choose some samples randomly versus you choose the samples as per the most difficult samples as per our acquisition, we will see that the accuracy improves more quickly for the orange strategy, which is active learning strategy, and there is a substantial gap. Now, here are the two things which we have to consider here. Let's first look at 200 labels. If somehow I had a budget of 200 labels, so then I'll draw a vertical line parallel to the y-axis. It will cut the blue curve and the orange curve. It cuts the blue curve at 79%, it cuts the orange curve at 91%. So, this is indicating that for 200 samples which I have labeled, my active learning strategy can give me a 12% improvement in accuracy. That is one way to look at it. Second, we can take a look at this. If I have a desired 90% accuracy of the system, so then I take a line, horizontal line parallel to the x-axis, I cut across this orange and the blue curve. It cuts the orange curve at about 175 labels required. It cuts the blue curve at about 500 labels required. So, if my desired accuracy is about 90%, I can get that with 175 labels as opposed to 500 samples required from a random strategy. Is this clear? So, these are the kinds of graphs you will see very often in a lot of presentations. I don't know how many of you have seen such presentations when Apple, let's say, reveals a new processor. So, they will say that for the same amount of power, how much amount of compute that they can increase, and for the same amount of compute, how less power they take with respect to the rivals. Okay. So, we now go on to the next issue. So, we have seen that we typically have this loop. In this loop, I label one example at a time, right? Now, could you think of any problem of labeling one example at a time? What could be a problem with labeling one example at a time? So, one, think of yourself as an annotator. Would you like to be poked every 3 minutes? Can you please label this? Can you please label this? Or you would prefer to? All at once? All the 10,000 examples at once? No. What is the something in between? You want to typically annotate a batch of examples. That is from an efficiency perspective, but there's more to it. There are more important reasons to think about a batch. So, let's say that if you want to label top 5 uncertain examples, we are still continuing the 3 versus 5 classification problem. Can you see that all of them are very similar to each other? Because the model doesn't have a very good understanding of these. So, if I just label based on the top uncertainty, I might end up looking at all similar examples. Is it very useful to the model? It's useful to perhaps have a subset of them labeled, but not all of them. That is not adding a lot of information. So, in contrast, would it be more beneficial to look at maybe slightly lesser uncertainty, but different diverse examples, like 4 versus 7, or 7 versus 1, or 8 versus 0, or 2 versus 7? Like here I am giving these titles 4, 9, 7, 1, 8, 0, that is typically not known beforehand. But from the probability, so if we predict a 10 class probability, we will get those numbers. So, it might be more useful to look at such examples as opposed to all of them which are very similar to each other. So, therefore, even though we are talking about hardest example, we also have to have a notion of representativeness as well as some diversity. So, therefore, if these were the different examples where we had a lot of uncertainty, we may pick up a diverse set of such examples which are uncertain. Typically, we end up using methods which are known as clustering to do that. It is a little out of requirement for this particular course, so I'll therefore not go in a lot of detail in that. But importantly, sometimes we can pick up examples which are not very hard, but we also want to maximize on the diversity angle. Yes.
So like you gave the example for multiple things, but we are training our model again after we annotate one of the examples. So I think it won't happen like we are continuously getting 5, 6 uncertain examples.
So here we are now talking about a batch. So here, that's an important question. Here we are directly acquiring a batch of examples to label. Previously we were doing one example at a time. If we do one example at a time, I think this problem will probably be to a lesser extent. But I get a batch of 5 examples, I want to label them. The batch of 5 examples which you pick, all of them are exactly this, 3s. So therefore, when you're labeling in a batch, you also want within batch, there has to be some amount of variability. Just one second. So therefore, we will, instead of picking up everything which is the most uncertain, we'll typically want to pick up which are conditionally uncertain, uncertain of given one example, conditionally uncertain. So therefore, we end up picking up a diverse batch. Sorry, there was a question. Yes.
So like you showed here that diverse batches we have picked up different digits, but like we could have confusion between 3 and 8 also.
We can have confusion between 3 and 8 also, yes.
That would be a diverse batch, right?
Yes, so here again, as I'm mentioning, so if you look at, based on that, if you look at the confusion between or the most probable classes, you could consider that as a feature to define the notion of diversity. You could also have some other notion of how to represent diversity or how to cluster the data effectively. Okay, now we'll discuss a few practical issues related to active learning, one of which I have already mentioned, which is known as the cold start problem. What do you typically understand by the cold start problem outside of the scope of this course? How many of you have driven vehicles in peak winter in north? Do the vehicles always start? Or even if not, if you forget about winters. So this is typically known as a cold start problem. The vehicle does not start when it is very cold. So therefore, on similar lines, the model will not be very good until unless you have labeled a few examples. But that is the whole problem. We don't have enough labeled data. So therefore, it's a catch-22 situation. Initially, the model quality will itself be very poor if you don't have a lot of labeled examples. And therefore, the uncertainty estimates you're getting out of the model are also not very reliable. So the way to think about this is to have enough samples across all classes labeled initially. If I have a 10-digit classification, I'll probably get the human annotator to label at least 10, 20 examples across each class. And then the model will be reasonably good to then give better uncertainty estimates, which would then be used for active learning. The second issue which we have to deal with is when do we stop? One heuristic to stop is when your budget has elapsed, which is a very trivial thing. The second is your accuracy is not improving sufficiently. So the delta accuracy that you're getting by adding more examples is very low. So therefore, perhaps it's not very useful to add. Or all the examples which you have are now more or less very certain. So there is not a lot of uncertainty left between them.
Can the accuracy decrease also?
Can the accuracy decrease? Anyone? Can the accuracy decrease of the system? Many of them are not deterministic, non-decreasing functions. So the accuracy can potentially decrease. It should ideally not. Sometimes you can also end up adding very noisy examples. So if the label itself is wrong of a particular example, and your model will undoubtedly find it hard to label it correctly. So therefore, the uncertainty of that example will be also high, and the label is wrong. So if you add that, that will probably add more noise, add more negative to the model than add some benefit. Thirdly, we also want to ensure that we have something known as stratification, or we want to ensure that each of the class has some good amount of representation in your label data. So perhaps if all of the hard examples come from any particular class, that might leave out the other classes. So if you're talking about a 10 class, maybe if all of the examples coming from 1, 2, 3, 4, 5, 6, but 8 is left, that will also not be a good data set. So you want to ensure that you get a reasonable proportion of samples across all of the classes. Typically how this is done is, when we don't have a lot of samples from some hard classes, you can, and they're not somehow picked by the uncertainty acquisition, you'll end up by random sampling from those rare classes. Finally, we have to think about batch versus sequential, and once we think about batch versus sequential, we'll also have to think about diversity versus just the most uncertain, so that we have some amount of variability in the batch and it's not all the same set of examples. Okay. So I had shown you one method of getting the uncertainty out of the models. This was when the model itself is making a prediction on the probability of classification. We are having 3 classes or 4 classes. We give the probability of class 1, class 2, class 3 and we get some probability. Then we can use some acquisitions such as max uncertainty or P1 minus P2 or the entropy. Could there be other methods of getting uncertainty? What could be any other method of getting uncertainty out of machine learning models? We have seen one case where the problem is something like a classification problem. So we inherently get uncertainty in the prediction by looking at just the probability values predicted. Yes. You would have to, sorry, is this a question or is this the answer to my current question? Okay, can you repeat your question? If you have to retrain, so by retraining, we don't really retrain a batch, we add a batch of examples to the training data set from the pool, which means that we will add x star comma y star for each of them. So we go back to this loop. So we do select x star equal to r max uncertainty of x. This is a single example. Instead of this, if we want to get a batch of examples, so we will get a batch, select x star batch, which would be some function here. Now you'll get a batch, let's say 10 such examples. So corresponding to 10x, you'll get 10y. You'll have to have the human being label those or some other method of labeling those. Once you have that, you will add those 10 examples to the label data set L and remove them from the pool. Okay, the other method of getting the uncertainty is to get multiple models. Previously, a single model was giving you the uncertainty. Let's say you have 4 different machine learning models. Again, you don't need to know the details of these. The first one is SVM, then random forest, naive Bayes, logistic regression. And the question was, it was okay, you want to predict the sentiment. So 2 of them say positive, 2 of them say negative. Can you see that there is a good amount of disagreement between the different classifiers? So therefore, this might be a good example to label. Right? So now you can do the entropy, you can calculate the entropy, or you can again look at the how many samples are positive, are predicted positive, negative across the different classifiers. So this particular method is known as query by committee. You create a committee of classifiers or machine learning models. Each of them will assign their own label, and then you look at how uncertain your entire labeled example is. Question on this? Okay. Thus far, we've been talking about the simple case of classification. How about regression? I want to predict the stock price of something, or I want to predict how many goals will be scored in a match. These are all regression problems. How much rainfall will happen today. How do I get whether or not I should be labeling such a sample? In probability, in classification was trivial because you could easily get the notion of uncertainty by looking at the different classes. Yes.
Take ensemble of multiple models and then just look at the standard deviation.
Okay, good. One of the trivial way to do that is create a committee there also. You have regressor 1, model 2, model 3. So model 1 says this house should be 40 lakh, model 2 says 60 lakh, model 3 says 45 lakh. You can see a lot of uncertainty in this. Whereas for house A, 50 lakh, 52 lakh, 51 lakh, a very less amount of standard deviation uncertainty. So therefore, we should probably be getting this example to be labeled by the human. That is through QBC, query by committee standard deviation. Similarly, we can get the predicted variance if it is coming from an ensemble of models. And then we will be leaving out, there are methods which will directly give you a notion of uncertainty, which in this case, an example which I've given is Gaussian process. We will not talk about that today.
Why would you be using, okay, so this question is like, why would you be using a machine learning model to label real values? So even if I was the labeler and you gave me a data set of the prices of houses and you didn't have those prices, how would I label it? I don't know the, if you gave me pictures of cats or dogs, I could tell you if it was a picture of a cat or a dog.
Yeah.
But I can't tell you by looking at a house how costly it is.
So you can't tell so not just the image. By the way, the input features are important. The input features are the area of the home, maybe the location. If it is in Gift City versus Kudas, then the prices would be differing by 1.5x.
Oh, so I am trained to do this thing. So
You are a property dealer. Yes. So that is how you have to think about such problems. In each case, the expert is the expert from the field. We have talked about different other examples also, named entity recognition as an example. So we looked at Apple announced a new iPhone in California yesterday. In active learning, now we have these different tokens. Each of them is given a specific label. Like in this case, our model predicts this to be either an organization or a product. It is confused. Is it a product? Is it an organization? So we can use these prediction classification probabilities to see whether this example should be labeled or not. Similarly, for object detection, so maybe this is a very simple example. The labeling is very well done, 95% confident, person 92% confident. But for this particular example, we are not sure whether it's a truck or a car. And the probabilities of this is 45% car, 40% truck. We should probably be labeling this. Similarly, for segmentation, we are not sure whether it's a road or it's a sidewalk. So we should again be looking at such examples. We have to also be a little careful that these are not as trivial as classification or regression. Here, because a single example has multiple tokens, should have to consider the uncertainty aggregated across each of them. This particular token is very uncertain, but the remaining tokens are very certain. So you have to think about how will you aggregate the uncertainties across multiple such tokens.
Will it take into account the other words classification also?
This one?
What Apple means?
Will it take into
Count the other words classification which we have done here while classifying Apple?
Okay, will this take into consideration the other classes that we've assigned to the different words or the different entities? That is dependent on the model. And what we are discussing, we'll keep it agnostic of that. Some models can consider the predictions given to the neighboring words. Some models will not. Will do it independently, or someone will build a dependent model. Okay, any questions on this active learning part? Yes.
So while deciding that which data we should label and which we shouldn't do manually, we still have to go through the entire data, right? Like, so it is just reducing our effort by certain
No, you don't have to go through the entire data. Let's say you have 100 samples which are initially labeled. On those 100 examples, you will create a machine learning model. That machine learning model will then make a prediction on the 10,000 samples which you don't have labeled. On those 10,000 examples which the machine learning will now make a prediction, you'll get the probability scores.
So amongst my complete data set, I need not label all the hard ones.
No, you don't need to label all the hard ones. You don't need to label all the hard ones. That is why we have to consider this specific graph. Something like this. How quickly can you get to the desired accuracy, or how quickly can you, for a given set of labels, how much quickly can you increase the performance? Other questions in the active learning part? Okay. So next we go on to the second method, which is known as weak supervision. Last row. Can you turn off your machine? Okay. So active learning, we had to have a human being give the entire label. In weak supervision, before I present this, we discuss this. What do you understand by weak supervision? Any guesses? Yes. Sorry? Weak heuristics to label the data. Not proper validation. Okay. So both of you are more or less correct. Let's consider some simple rules of thumb to decide whether or not something is a positive or a negative example, right? So if you find the word good in a review, is that going to be largely positive review? Do you think that? Maybe 8 out of 10 it will be a positive review. When can it be a negative review even though it has the word good? Not good. Right? Similarly, if it has a lot of exclamation marks, what do you think? Will it be good or bad? That will show a lot of polarity. Typically very positive, but it can be very negative also. Pathetic product, exclamation, exclamation, exclamation. So we can create such very simple rules of thumb to get a sense of what the prediction might be, what the label might be. We will then be using multiple of these weak rules through some principled methods to get the final probabilistic prediction for that or label for that particular example. Let's look at this. So if we take such simple rules, it is positive if the word love is in the text. I absolutely love this product. And negative if the word terrible is there. The product was terrible. If the number of exclamation counts is greater than 3, then it is a positive label. Otherwise, abstain from giving a prediction. So LF means a labeling function here. We could have said amazing, love, masterpiece, positive, boring, waste, terrible, negative. If the rating is, if someone gives a rating, my rating for this movie is 8 on 10 or 2 on 10, that can also perhaps tell you whether it's positive or negative. If they mention Oscar, then probably positive. Again, someone can write it in a negative sense also. This movie was so pathetic that it should be recommended to the Oscars. The length, very short review is often negative. I didn't like this movie. If you like a movie, you will perhaps go the length to write a positive review. It can go in the other way also. It goes with the course feedback also. So I've seen that. What did you like about this course? The classroom. It was but that was a very positive review overall. Now, when we have these different kinds of labeling functions, we have to think about the diversity that they represent. If we see such functions, such as if good is in the review, so this will probably, good will be there in a lot of reviews. But if you pick up a labeling function which is more precise but rare, like if the IMDb rating is greater than 9, if they mention that this movie has a rating or if the IMDb rating is somehow present, is greater than 9. So this will likely be available in a lot less number of movies, but wherever it is available, it will likely be very positive. It will probably be very correct. So therefore, this is precise but rare. On the other hand, you can have functions which are broad but noisy. Good, so good movie, correct, it is a positive. Good effort but failed, it is again predicted to be positive, but it should be negative. Not good, again it is predicted to be positive, but it is negative. So therefore, we somehow need to take all of these multiple labeling functions which we have created and somehow combine them, where some of them give you good coverage like this one, some of them give you good accuracy. You want to overall create something with good coverage and accuracy. When we think about the kinds of such functions, we can think in terms of keywords. Amazing, excellent, loved, great is present. If these keywords are present, it is positive. Heuristics, if the length is very short, it is a negative comment. We can load some amount of external knowledge. If it is an IMDb top 250, then it is a positive if the title is there. But importantly, many times they will disagree. Different labeling functions will disagree. I love how terrible this movie is. So it contains the word love, so it should be positive. It contains the word terrible, so it should be negative. What do you think should be the overall label for this? Yeah, probably negative only, just the way it is written in, yes, it's a very sarcastic comment. So we can, in libraries such as Snorkel, we can create these abstain, negative, positive, assign them some numbers -1, 0, 1 and create these kind of labeling functions. Eventually, out of Snorkel, we will get the, if we run it through such tools, for these unlabeled data, we have multiple labeling functions. It will go through some intrinsic, some processes, which we will study. Eventually, for each of these samples, we will get the positive, negative classification probabilities through some simple rules that we used, which are known as soft labels. Now, we will see how we can get something like this. Let us take these 5 examples. Some of the rating is also available. So, the first labeling function is if good is in the text or not, then vote positive, otherwise abstain. And second is the rating is greater than 7, then vote positive. If less than 4, vote negative, else abstain. So, if we look at the first example, good movie, it will be labeled positive by LF1 because the word good is there. LF2 will also rate it positive because rating is 8. Good but boring, it is the word good is mentioned, so LF1 will label it positive. LF2 will not label it because it labels only bit greater than 7 or less than 4, and this is a 5. Terrible, it will be labeled negative, but it is not, there is no mention of good here, so LF1 will abstain. Decent, LF1 will abstain. LF2 will give it positive because the rating is 7.5. Good but poor, good is present, so therefore LF1 will get positive. The rating is 4, not less than 4, so therefore LF2 will abstain. Now, if we look at these functions, LF1 will fire on 60% of the examples, and the labeling function 2 fires on again 60% of the examples. So, the coverage for both of them is 60% each. Yes. So, we had looked at that as a specific task also. You can have functionality specific sentiment also. So, that will be a separate task. But whatever we are doing today is again going to be agnostic of the kind of task. This will be a more general framework. You can again do the same exercise on a functionality specific behavior as opposed to on the overall review, and you should still get similar. The framework, underlying framework should still remain the same. Okay. Now, the first metric which we looked at was coverage. How many examples are covered by the different functions? LF1 60%, LF2 60% in this case. The second is the overlaps and conflict. Firstly, LF1, LF2 for the first example, they both voted and they agree. Both of them said a positive. And we don't have any other examples where both have voted together. So therefore, if we look at the overlaps between the two labeling functions, the overlap is 100%, is only for one example, but on that the agreement is 100%. So we will now be looking at better methods or some a slightly bigger data set to try and understand how much trust should we give to LF1 and how much trust we should give to LF2. So if you were sleeping till now, please wake up. The next segment is a little bit more involved than the previous things. We will be using a variable called alpha to denote the probability that the labeling function is correct when it votes. So let's say that if for labeling function 1, alpha 1 is 0.8, it means that when it is voting, means it is not abstaining from voting. It is correct 80% of the time, and similarly LF2 also, perhaps when LF2 votes, it is correct 90% of the time. So we somehow want to estimate these quantities alpha 1 and alpha 2 from our functions themselves. So let's assume that we applied these labeling functions to 1000 reviews. LF1 fired on means it voted on 300 reviews. LF2 reviewed, fired on 250 reviews. So 30% and 25% are the coverages. Both are firing. So the intersection between LF1 fired and LF2 fired is 100 reviews. And out of these 100, they agree 85% times, 85 samples, and they disagree 15 samples. So therefore, on this 1000 review data set where we have 100 common firing or overlap, the agreement is 85%. Right? So therefore, you can see all these terms. LF1 coverage 30%, LF2 coverage 25%, overlap 100 on 1000 10%, and the agreement on the overlap for these two functions is 85%. Now, we have to think about when are these two labeling functions agreeing. Can someone tell me what are the cases in which they are both agreeing? LF1 says positive, LF2 says positive. LF1 says negative, LF2 says negative. These are the two cases. So both are saying this to be positive. In that case, we will have the probabilities to be alpha 1, alpha 2 into alpha 2, and similarly if both of them are wrong, LF1 wrong and LF2 wrong. So the probability of correctness was alpha, not the probability of positive prediction. Both of them correct, right, probability is alpha 1 into alpha 2. Both of them wrong is 1 minus alpha 1 into 1 minus alpha 2. The probability that both of them will agree is alpha 1 alpha 2 plus 1 minus alpha 1 into 1 minus alpha 2. And we had observed from the data that the overall agreement was 85%. So therefore, 0.85 is equal to this alpha 1 alpha 2 plus 1 minus alpha 1 alpha 2, 1 minus alpha 2. Can we solve for these alpha here? Why not? So therefore, what kind of a problem is this? Underdetermined problem. How many solutions can you have for this? You can potentially have, infinite solutions for this. Now, when we look at 3 labeling functions, we somehow added another labeling functions. Now we have these 3 pairwise agreements. LF1, LF2 have 85% agreement, LF1, LF3 80%, LF2, LF3 90%. So therefore, now we get 3 equations, 3 unknowns. Can we solve them? I will be solving this using PyTorch. Again, just one second. Let me first just run this. I'll get back to the question. The observed agreements between them are 0.85, 0.8, 0.9. This is what we'd expect to get. I will say that I want to somehow learn these alphas given the data. I will somehow use an optimization procedure to learn these. I am doing a bunch of tricks here, one of which is known as a sigmoid transform to convert them on a scale of 0.5 to 1, but those are not particularly important. So, here is some iterative procedure which is trying to reduce the gap between my predicted agreements and my agreements which I am getting from the data. So, the agreements I am getting from the data are 0.85, 0.8 and 0.9. So, I have to choose values of alpha 1, alpha 2, alpha 3, which if I run through this optimization procedure, I will get 0.85, 0.8 and 0.9 by doing these calculations. And if I run this over several iterations, I will see that I am able to learn these, like LF1, LF2 agreement was 0.85 with my chosen alpha 1, alpha 2, alpha 3, which is 0.86, 0.98 and 0.91. The predicted verification, the predicted agreement between them is 0.85 almost. This should have been 0.8, this is 0.88007, this should have been 0.90, this is 0.8995. But through this procedure, importantly, I have been able to learn alpha 1, alpha 2, alpha 3, which is what I was trying to do. There are multiple methods in which this could have been done. So, the library which we will be using does not use this kind of a procedure, but this is perhaps one of the easiest way to learn these parameters. Sorry, was there a question?
Sir, in the notes you have added, you have written that rating less than 4 negative, but didn't we have the same thing in LLM?
Just an example. You can have another example. It could have been anything else. So, typically we will want 3 functions, labeling functions to solve for accuracy. We can't have 2 because then it will be underdetermined. Typically, if we, even if it is more, we get n choose 2 pairs with n unknowns. So, therefore, it becomes an overdetermined problem, and we are able to cancel through the noise in order to get the alpha values. Okay. Now, once we have got these alpha values, we still do not have a way to predict the labels. We need to do something more. We compute something known as the log odds of accuracy, which is W equal to log of alpha minus over 1 minus alpha. So, if this was 0.8, then my weight will turn out to be 1.39, and if it were 0.9, my weight will turn out to be 2.2. So, if alpha is more, which means that my labeling function is more accurate, it means that I should give it more weightage, right? That function should be given more weightage while deciding what is the overall correct label. So, that is how we will be ending up using this weight factor. So, eventually, if we had this text, good movie with a review of 8, IMDb of 8, LF1 had voted to be positive, LF2 also voted it to be positive. So, in that case, my W1 was 1.39, W2 was 2.2, I will just add these and my score for negative is 0. Similarly, for good but boring, LF1 voted it to be positive, LF2 did not vote, my score for positive is 1.39 and score for negative is 0. Terrible, LF1 abstains, LF2 votes it negative. So, score for positive is 0, score for negative is 2.2. Similarly, the last one, decent film, LF1 does not vote, LF2 votes it to be positive. So, the score for this is 2.2. Now, for each of these 4 examples, I have score positive and score negative. These are the weights I have calculated. So, after that, I will do e to the power 3.49. So, just bear with me for the formula. E to the power 3.59 divided by e to the power 3.59 plus e to the power 0 which will give me 97.3.973 as the probability of positive. This one is 1.39 and this one is 0. So again, e to the power 1.39 divided by e to the power 1.39 plus e to the power 0 gives me 4 divided by 4 plus 1, which is 0.8. E to the power 0 divided by e to the power 0 plus e to the power 2.2 gives me 1 over 9, which is 10%, and similarly for the last example I get 0.9. So through these examples, so third one, the probability of positive is 10%. That is because third one we got only one vote from LF2, LF1 did not vote, and LF2 has a good weight, 2.2. LF1 has a slightly lower weight because the alpha 2 value is very positive. Given that, we will assign it to the probability of positive to be only 10%. So if we see, both the labeling functions were agreeing, very largely positive. Only one of them is agreeing. So this is 90%, this is 80%, this is 90% because this is coming from a stronger labeled function, this is coming from a weaker labeled function. Similarly for this. Okay. So finally, when we want to train, we can make use of these soft labels. We could also just do a simple binarization of them. Greater than 50%, the label is positive. Less than 50%, the label is negative. You can do some soft, you can just do some hard thresholding on this. So to summarize weak supervision, if the patterns can be encoded as rules, please, we should be going ahead and using such weak supervision methods. If you have domain knowledge and if the heuristics are very clear, sometime when there is a lot of human detection, human judgment required, whether it is humor or sarcasm, in those cases weak supervision will not work, and the data set is very small, you should just label it yourself. Questions before we go into the last part? Okay. So in this part, we want to discuss LLM-based labeling. This should be the most fun part for you, I think. So LLMs can label data because they have been trained on almost all of the internet. That is what we are trying to, that is what they claim. On huge data sets, billions, trillions of examples, and they consist of different kinds of things, movie reviews, social media, news articles, Reddit, academic papers. So they have seen a lot of content, and this is somehow distilled into some models. This entire knowledge base of humans is somehow distilled into model. Let's just look at an example. If on ChatGPT I give this question, label sentiment positive, negative, neutral, this movie is not too bad. It labels it to be positive. This is the simple LLM labeling tool. Could you use this for 10,000 examples? Why not? Time and money. Why will it require more time? Yeah, so how big of an PDF assignment have you pasted into ChatGPT and realized it does not work? There is some limit to it, right? The amount of tokens it can process. So maybe not 10,000 movies, but a smaller number of movies it can. In this case, I labeled a single movie. Can I label multiple movies? Right? So how do I label multiple movies? Multiple times like this. So labeling multiple movies, I could do this and this. So 2 movies, 2 prompts. Could we do something better? We could do batches. So now we'd say label Why is it beneficial to do in batches? Sorry? Okay, one is less number of requests. So that is from perhaps a network's perspective. You're saying something else? No. So look at this. Is this text repeated? Can we save that? In this, we are not repeating that. So therefore, typically when we look at the request which we send, it is typically two parts, the system as well as the user prompt. Right? So typically what you want to have something agnostic across multiple requests, you can call that to be the system prompt. And something which was specific to that request or to that user's request, you can have it as a user prompt. So I can create batches like this, but even this will get boring after a time and this will get very redundant after a time. So therefore, we should perhaps wherever possible be using the API. So going back. So maybe we have two different roles. The system role is to classify the movie reviews as positive, negative, or neutral. And then the user role is to define the mind-blowing visuals. Nolan does this again. This is a question, and you want to get back the response as positive. So therefore, system typically defines the task persona in our output format. But have I given any output format? No. Yeah. So what might be a So maybe we want to give a JSON response. Actually, I forgot to give the movie, but it's still remembered. So ideally what we want to, this is the system prompt. And then this is actually this is not ideal. I would have wanted, I might have wanted an array. Yeah. So we want arrays of this JSON objects, query, sentiment, query, sentiment. So I have defined in the system from the persona, but the persona can be further modified. I don't know if this changes anything or not. See, went from positive to neutral because now you have defined the persona. But this is also limited. Ideally, you want to have usage of some API. We will figure out some way to get you free API. What is that? Open router, I think. So if we look at open router, we should perhaps get some models which are free.
You could run it locally in Prof.
we could run locally with Ollama, but not everyone can run locally with Ollama depending on system configuration. But we can get these free, we can get the free endpoints. So we'll perhaps do this in the lab. After that, your rate of submitting assignments should improve or get worse. We'll see. The other important thing which I think many times we miss is known as few shot prompting. So there we want to give a few examples of if loved it is positive, terrible is negative. If we give this, this also inherently defines the persona that we have. It makes it slightly easier for the LLM to do the classification. The LLMs may struggle when there is a lot of subjectivity involved, where the persona is not very clearly defined, when the categories can be very nuanced, like very negative, negative, neutral, positive, very positive, and when the guidelines are also ambiguous. What counts as slightly negative? Again, it's not very clear. Let me see. Okay, there are a couple of more things, but I think we can do them in the next lecture. So the announcement, I shared the announcement for the quiz.